This is going to be one of my most theoretical videos in this lecture series on genotype. The fact is that to be a good farmer, from what I've noticed, you really don't need to know much about genetics. I remember chatting with a very successful farmer, and he attributed his success in the relatively dry 2020 growing season to planting a variety of corn that was drought tolerant. And he said it was drought tolerant because it had a gene from a cactus in it. Now, that's wrong in about 8 different ways, but he's still a very successful, very innovative, and progressive farmer. So I say this with respect, but you clearly don't need to know very much about the science of genetics or biotechnology to be successful. But having a bit of background can make you a more discerning customer and prevent you from being misled by erroneous marketing claims. So while a farmer does not need to be an expert geneticist, they do need to be very smart about variety selection, selecting varieties that are adapted to the environment, the farms that they're in, as well as adapted to their particular management style. And there's a number of things to consider. Depends on the farmer. I'll give you one example. I was chatting with a farmer who grows a lot of white beans, edible beans. That's his main focus, and he'll rotate with corn. So he's not choosing corn varieties that are highest yielding or best adapted to the environment, so to speak. He is choosing corn varieties that are not going to interfere with his white bean management and his white bean crop. So in other words, he selects shorter season varieties of corn that are adapted to his environment, and he's making sure that whenever he has to harvest or any other spraying, whatever management activity in the corn will not happen at the same time as the white beans, because that's his focus. So the variety has to fit the management style as well as the environment. Other high-level ideas. In the marketing materials, you can often see companies are simplifying things, saying that very complex traits like yield or drought tolerance are controlled by a single gene. So they inserted a gene, or they're increasing promotion or expression of another gene, and that's causing higher yields or whatever. That's a major simplification. What is true is that single gene transgenes or single gene insertions can confer, say, herbicide tolerance or tolerance to or expression of Bt, but a single gene does not control yield or drought tolerance. There's multiple genes and gene expressions involved in those traits. Another high level is that it used to be in the past, corn and soybean varieties were on the market for 8, 9, 10 plus years. And so farmers would not turn over their corn varieties very often. They'd be growing the same variety for 5 plus years in many cases. That's changed. Just the speed of introduction, companies are taking hybrids off the market within 3 or 4 years of introduction, replacing them with a newer one. And so farmers are growing, newer varieties in corn and soybean. That's not true with small grain cereals as a general rule. First off, varieties are not released as often. The amount of breeding investment is less in your winter and spring wheats, your oats, barley, whatever. Also, farmers are legally allowed to save seed in many cases. So they'll grow a wheat or barley crop, they'll save some of that seed to plant the next year. And so they're using the same cultivar. They're not necessarily buying in seed that can be more expensive. But that said, this is changing as well. It is not uncommon to see farmers growing, say, 20-year-old varieties of oats or whatever, but the newer varieties are just so much higher yielding that once farmers kind of see it for themselves, they'll often make the switch and they'll buy the more expensive seed because it is just so much higher yielding. There's growing interest in what is called hybrid-specific management. So let me back up. There's no real pre-breeding strategy to fit a hybrid to a given management system, be that tillage versus no-till or high versus low plant populations or whatever. Breeders are basically looking for high and stable yields across multiple environments. That's a very heavy selection pressure that they're putting, and only hybrids that pass that selection or varieties that pass that selection pressure are even given consideration for going into commercial release. So once you get high and stable yielding varieties, then farmers and agronomists are looking at trying to fit those varieties to particular management styles. Again, that can be different plant populations, different tillage or whatever, but you have to figure that out yourself because the breeding companies are really focused on just getting high yielding, stable yielding varieties out there. And so there's now growing interest in Ontario in hybrid specific management. Which hybrids respond to fungicide the best? Which hybrids are best at high or low plant populations, or what have you? This has to happen after the fact. And again, you only have 3 or 4 years to figure it out because then that hybrid's replaced. But there's growing interest in hybrid specific management. Before we talk about workhorse versus racehorse horse hybrids and yield stability and phenotypic plasticity and all that fun stuff, I need to give my little agronomy caveat, which is, genetics super important. No one's going to dispute that. But I think there's been an over-promising and under-delivering, especially on the research side and looking at where research dollars are going. There was a huge promises and huge investments in molecular genetic techniques, basically trying to insert a gene or find a gene that's going to confer drought tolerance or higher yielding or something that can increase gene expression to increase yields. And there's been tons of investment, and not a huge amount of things have been delivered. And that has to do with what I would think is a faulty paradigm, which is that, yield is a function of genes only. So it's a bottom up approach. We get the genes right, we get good genes, and then we're going to get good yields. We cannot make those inferences. And I give you an example here. This is from a study of identical twins. These are identical twins. They have the exact same genome, and one of them works out and one of them doesn't. And you can see obviously what's going on here. The twin that works out is just completely buff, and the twin that doesn't is not. And the point here is that you can have the exact same genome, right? And these varieties or cultivars will have the exact same genome, but environment and management is going to alter gene expression. And so you can have the same genome, but those genes are going to will be expressed at different levels or may not be expressed at all, depending on what that management is, right? If you're working out or not, depending on your tillage, if it's a dry year, a good year, a bad year, whatever. And so we cannot make inferences from the gene to the crop yield. There is no privileged level of causation in agronomy. We can't say, oh, we've changed genes, so we're going to get a change in yield. You cannot do that because at the yield level, at the crop population level, differences in management and environment are going to feed back into what genes are being expressed. So that's my little agronomist kind of caveat. Apologies for going on a bit of a tangent there. Let's return back to cropping systems. Let's first start with the first one, yield potential. So this is the genetic yield potential of a crop when grown in non-limiting conditions. So we're not imposing any nutrient stress, abiotic stress, or biotic stress. We're allowing the genetic yield potential its fullest expression. And we can estimate genetic yield potential by looking at record yields from yield contest winners. For example, non-irrigated corn yield contest winners typically get yields around 300 and 400 bushels per acre. That contrasts with what is in Ontario average on-farm corn yields of about 170 bushels per acre. That means there's clearly a yield gap between what's achieved on farm and what's possibly achieved with today's genetics. Of course, the implication is that there's environment and management factors that are reducing actual yields below genetic yield potential. Yield stability is a genotype-specific trait that measures, as the word implies, how yield varies across environments. And environments, again, is just a scientific $5 word for growing season. So how does yield change over growing seasons? Is yield stable or is yield unstable? Now, there's two different measurements of yield stability. There's static stability and dynamic stability. And farmers and breeders typically use different definitions. Most people think of yield stability in the static sense. That is, that across growing seasons, a variety that is highly yield stable is just going to yield the same each and every growing season. So in really stressful growing seasons, in really favorable growing seasons, yield basically the same. That's a yield stable variety. Static yield stability is what we would call an absolute measurement. So it doesn't really depend on the yield of anything else other than the variety under question. And you can measure static yield stability, for example, by calculating the coefficient of variation or standard deviation of yield across different growing seasons. Dynamic yield stability is a little bit tougher to define because it's a relative measurement of stability. you can only calculate the dynamic stability of a variety in relation to or relative to other varieties grown in that same variety trial. So if you did a variety trial over many years, you would have some years that were low yielding, stressful, some years that were medium, and some years that were high yielding, favorable growing seasons. And you can see an example of that on the right, this figure from Leslie's paper. A dynamically stable variety is going to have close to average yields in every one of those environments or growing seasons. And that means that its stability is defined in relation to the trial average, what other varieties are yielding. We can define stability, either static or dynamic, mathematically by looking at or calculating the slope of the line of a graph, like you see here, grain yield as a function of environmental index. And so it's possible to define stability mathematically. We won't do that in this class, but it's going to be important for you to be able to look at a graph like this one, look at the slope of the line, not calculate anything, but tell me, is this a dynamic or static stability variety? Another point is that yield stability has nothing to do with yield level, right? You can have a variety with consistent yield of 0, a consistent yield of 1,000 bushels per acre. Those varieties will have the same static yield stability, basically perfect yield stability with 0 deviation or variation. Variety selection is one of the more difficult decisions that farmers face. They have to make this decision every year, and especially for a crop like corn or soybeans, it's a major financial investment. And so seed companies obviously try to convince farmers, they try to market to farmers to buy their product. Okay, and so one of the ways that seed is marketed, corn seed especially, is that these varieties are placed as racehorse varieties or workhorse varieties, or aggressive and defensive varieties. And the value add for the farmer is that they can choose these select a variety based on things like their field's yield potential or their management style. So there's no obvious, or I should say well-defined definition of what a racehorse or workhorse variety is, but from what I understand, a racehorse kind of corn hybrid is one that has very high yield potential, and it does well on your best land and responds to intensive high input management. However, it cannot handle stress as well. Your workhorse or defensive variety or hybrid handles different kinds of stress as well, but does not have top end yield potential. So we just talked about yield stability, static and dynamic. And this distinction between workhorse and racehorse varieties kind of jives with this idea, right? You can have your racehorse varieties with low yield stability. They either do really well or really poorly. And a workhorse that is very stable. It kind of yields consistently across different environments. So there is at first glance scientific evidence to support this distinction versus racehorse and workhorse varieties. But it could also just be used as a post hoc explanation. For example, if a variety performs poorly, someone can come by and say, well, that variety is more of a racehorse. So let's use some science to critically evaluate, see if there's a scientific basis for this racehorse versus workhorse distinction. Keep in mind that yield stability is not necessarily desirable from the perspective of the farmer. Say you have genotype 1 and 2, and genotype 1 overperforms in certain kinds of growing seasons. Well, genotype 1 would be considered lower yield stability, right, because its yield is more variable than genotype 2. But a farmer would always pick genotype 1 because it yields just as well as genotype 2 in 2 of the 3 environments, and genotype 1 yields better in 1 of the 3. So this racehorse genotype 1, lower yield stability, would always be the best decision. The next thing to keep in mind is that for this distinction between workhorse and racehorse varieties to be valid, there must be a trade-off between yield stability and yield potential, and also between yields in favorable and unfavorable or stressful environments. So here we have an example where there is a trade-off between yield stability and potential. Genotype number 2 has consistent stable yields across all environments. Genotype 1 has much higher yields in this high environmental index, so a favorable growing season, but much lower yields in the low and medium environmental index, and we can just call those stressful years. And so in this case, there's a clear trade-off. A farmer needs to make a decision between what kind of variety that they want to plant. In this scenario, yield is always higher in genotype 1, although yield is always more stable in genotype 2. So for a farmer, no matter what the environmental index is or whatever that growing season happens to be, they're always better off selecting genotype 1. Anyway, this all brings us back to the original point, which is that for the distinction between racehorse and workhorse hybrids to be valid, there has to be a trade-off between yield potential and yield stability. In 2002, University of Guelph corn breeder Liz Lee and corn physiologist Thijs Tollenaar tested this idea that it's worthwhile for someone to distinguish between racehorse and workhorse varieties when selecting a variety to grow. Their hypothesis that there was actually, in fact, no relationship between yield potential and yield stability, either a positive or negative relationship, and so this workhorse versus racehorse distinction wasn't all that useful. What they did was they took hundreds of yield data points from around the USA, from large variety trials, but they only focused on looking at varieties that were used by yield contest winners. So essentially they took those varieties that yield contest winners used, they looked for those varieties in large data sets of variety trials, and they calculated both yield potential and yield stability. So the authors calculated dynamic yield stability as opposed to static yield stability. And you can see a visual representation of their hypothesis here. So they took the variety trial average yield and they plotted the slope of that, right? The average variety trial yield in different environments, high yielding and low yielding site years. And then for individual varieties, they compared the slope of how yield changes with environment to the variety trial average. So varieties that have a much steeper slope compared to the variety trial average, those are racehorse varieties. In low yielding years, they do much worse than average. In high yielding years, they do much better than average. And varieties that have a shallower slope than variety trial average are workhorse varieties. More stable yields, they yield a bit higher than average in low yielding environments, and they yield lower than average in high yielding environments. So their hypothesis looked like this, that there were varieties that were more higher yielding and also more stable than the trial average. So in red, you see this workhorse variety, more stable yields across environments, but also higher yields across environments. So what these authors did is they calculated the slope of yield across different environments. In other words, they calculated the dynamic yield stability of varieties and also its average yield. So what did the researchers find? Well, when they looked at the varieties used by yield contest winners in the United States and Canada, they found that those varieties were more workhorse than racehorse. Those varieties had high yield stability across different environments, but also really good yield potential. They also found that modern elite hybrids do vary in terms of yield stability. So there are varieties that are more stable in terms of their yield. However, they found no evidence that yield stability and yield potential are mutually exclusive. There are varieties out there that have high yield stability and high yield potential, so you can have it all. Now, this is not to say that there are not important G by M interactions. For example, there might be some hybrids that do better at higher seeding rates or planting densities than others. And you got to figure that out. But the point is that these varietal responses to different management practices has nothing to do with yield stability or yield potential. There are other traits involved in creating those genetic responses to management. Central to understanding G by E interactions is the concept of phenotypic plasticity, which is the definition of environmentally contingent trait expression. So we can think of any crop trait, be that yield, rooting depth, leaf area, as being regulated by the environment as well as the genotype. And the more phenotypically plastic a trait is, the more that trait is regulated, its expression governed by the environment. Crop traits that are stable from season to season and aren't very much affected by things like weather, those traits would not be considered phenotypically plastic. They would be primarily regulated by the genotype as opposed to the environment. Now, hopefully you understand how the concept of phenotypic plasticity can be related to either static yield stability or dynamic yield stability. And this is something you should be knowing for future assessments in this course. A good example of a trait that's phenotypically plastic is rooting depth and root length of cereal crops like corn or wheat. Those crops generally respond to drought stress or nutrient stress by increasing rooting depth and branching out, exploring more soil, basically creating longer, more branching roots. There's an obvious reason why a crop would do that, right? Well, hey, I'm under water stress or I need more nitrogen, so let's invest more in those root structures to find some of these nutrients. But maintaining those sensory pathways that detect, hey, drought stress is occurring or hey, nutrient stress is happening, that pathway is energetically costly to the plant. The plant has to manufacture hormones and maintain specialized cellular structures for this phenotypic plasticity to occur, for there to be a way to understand or sense its environment. And that might not be rational, quote unquote, from the plant's perspective if, for example, it knows it's always going to be grown in a dry environment. Why maintain those pathways to say, hey, is this a dry or wet growing season if it's almost always going to be dry? It might make more sense for that crop to have evolved a specialized root system to always root very deeply with a highly branched system, because it quote unquote knows via evolution that it's almost always going to experience dry conditions, so might as well specialize for those environments and not really invest in the sensory network. The root system of sorghum is an example of a more specialized root system, in their case, or in that case, specialized for dry environments. Sorghum evolved in an arid area of Africa, and so its root system is generally always more deeply rooting, always more branching. It's specialized in those dry environments. Even if it's grown today in an irrigated system, its root structure is adapted or specialized to those drier environments, and it's going to be less phenotypically plastic in response to water supply.